Hi guys, this is GKCS. We are going to be talking about bitwise manipulation now, and this topic is something that I really love because it makes the efficiency of your program go like off the roof if you get it right. So this topic comes up in competitive programming in strange places. Sometimes you don't expect that this could work, but it does. So if you have seen the NP hard problem on CodeChef, NP complete problem, which requires some sort of approximation algorithms to get right, that's a place where this kind of optimization might help. In AI contests, for example, in Hacker Earth, more often than not, I am representing the board, the entire game state, using these binary values. So, for example, let's take this board. It's a 5 cross 4 board, and if we store every integer in this as a 32-bit integer, then it's going to take quite a bit of space. But what we could do is we could observe the board, understand that each value is associated to a single player. So if it's 0, nobody has claim for that cell. If it's 2, then player 2 has claim on that cell, and player 1 otherwise has claim on that cell. So what are the numbers that each cell could take? A cell can take values between 0, 1 and 2. It can take 3 values basically. So instead of taking 32 bits, you could just take 2 bits to represent 0, 1 and 2. That's over here, 0, 1 and 2. That's it. 3 bits. And this value of 3 will never be used because the cell doesn't take that value. So from 32 you brought it down to just 2 bits. That is 16 times lesser. So basically whatever space requirement you had S is now S by 16 now. So that is more than 90% savings in terms of space. Now you might think that space doesn't really matter because we have that much RAM, but not always. And secondly, allocating that space and checking for each position in this matrix costs you time. So the constant factor of 16 is pretty big when you're going for cutthroat AI contests. Alright, so this bitwise manipulation is pretty important, and let's have a look at how to do it. One of the most common use cases for binary manipulation is when you have an input 2D matrix and you need to convert it into a binary number. Firstly, this input 2D matrix needs to be converted into something that we are very familiar with, a 1D matrix or an array. So we come to the first index, which is 0, 0, and this is how we convert this 2D matrix into a single array. You take the row number and you multiply that with the length of each row. So that is row number into length of each row, so that is len row, let us say, plus you add the column number, and this gives you the index of the element which is in your 1D matrix now. So this is your current index, which is equal to this. So using this formula, let's go for 0, 0, the very first element. 0, row number into whatever, doesn't matter, plus 0 gives you are at this index now. So this value needs to be mapped over here. So let's do that. 7 comes here. What about this? Row number is still 0, so this product will be 0. And column number is 1. So what do we have? Plus 1. So we have to come here. And basically what you're doing is you're just taking each row, grabbing that slab, putting it over here, and then taking the next row and putting that slab next to this, and so on and so forth. So however big your matrix is, it doesn't really matter. Using this formula, you're converting into a 1D matrix. What about this? Row number is 1. So the length of each row is equal to 2. 1 and 2. So 1 into 2 gives you 2. Plus column number is 0. So this is 2. Okay. Yeah, the index is 2, but you need to map this element. So that element goes over here. This element finally will go over here using the same formula. Now that you have the 1D array, let's convert these into binary numbers. 7 in binary is equal to 1, 1, 1. 3 in binary is equal to, 1, 1. Okay. 4 in binary is equal to 1, 0, 0. And 6 in binary is equal to 1, 1, 0. But that's not all. In the computer, you'll be requiring around 32 or 64 bits when you're storing this. Usually 32 because you have these as ints. But depending on the data type, you'll have a lot of wasteful bits. So what I mean by that is there'll be lots of zeros over here. In this case, 32 minus 3, which is 29 zeros. And then you have the 1, 1, 1. Here you have 30 zeros. Here you have 29 zeros again. And again here you have 29 zeros. So you see there's a lot of space being wasted. What you could do is crunch all this space, basically get rid of all these zeros, extra zeros, and push them together so that you get this really small number, really nice informative number. Now when you're doing this, of course, you need to be careful about a few things. Firstly, you see here that there are 30 zeros over here, but we basically need to look at the maximum value that we can have in this array. And once we know what is the maximum value, then we can make a judgment on how many zeros we can actually skip when reading a number. So in this scenario, our maximum value is 7. Or let's have a look at this array. Maximum value is 7. 7 is the number. Understand that we are dealing with binary. So we are looking for the number of bits, the minimum number of bits which can contain this information comfortably. So 2 raised to the power n minus 1 has to be greater than or equal to this number. We are looking for this n. Why? Because when you take 1 bit in binary, it can represent 1 or 0. When you take 2 bits, it can represent 0, 1, 2 or 3 and so on and so forth. So if you take n bits, you can represent 2 raised to the power n minus 1 values from 0. And so basically the maximum value has to be less than or equal to that. So using this formula now, this is a new formula that we have, we are going to find the number of bits that we need. So every element here will have n bits. Let's go for n. What can we do to find about n? Should we use binary search? Yes, you can. You could use binary search here to find out the right value of n. But would that be sensible? Not really. Rarely is it sensible to put binary search in this case because you're going to hit n very fast. So let's just do this to show an example. Let's take n equal to 1. So 2 raised to the power 2, which is 2 raised to the power 1, which is 2 minus 1 is equal to 1. Oh yeah, 1 bit doesn't contain any information. So it contains one element. It can represent one element. 2 raised to the power 2 minus 1 is 3. 2 raised to the power 3 minus 1 is 7. And this function goes up very fast. So it goes up at an exponential rate. At 2 raised to the power 32 minus 1, you are near 2 billion. So you understand that the maximum value contained here will be hit in log n time. You can work out that and probably understand why it's hit in log n time, but because this function goes at an exponential rate, you hit the maximum value very fast. And so in 3 bits, we can represent 7, which means in 3 bits, we can represent any element in this matrix. Why? Because 7 is the maximum value. It will require the maximum information possible to represent itself. Therefore, in 3 bits, we can represent any element in this matrix. Alright. So we require 3 bits, which means this is okay. We are using 3 bits. This is not okay. We are using just 2 bits. So we need to actually add a 0 here and say that we have 29 extra zeros over here. What about this? This is fine and this is fine. Okay. So all that's left to do is to take these numbers, get rid of the useless zeros, squash them together and put it into this binary value result. So the way we are going to do that is by using this code. We have already found that the block size required per binary element is 3. And so we are going through every element a of I, which I goes from 0 to n minus 1, and we are left shifting by a particular margin. So this left shift margin is something that we'll look at right now. Let's take the first element, 7. 7 in binary is 1, 1, 1. We have the binary value being set to, at index I equal to 0, binary value is set to binary value, which is initially 0, plus 7 left shifted by I, which is 0. So 0 into anything is 0. So it is not left shifted at all. So A of I is 1, 1, 1. And binary value is 0. So binary value is set to 1, 1, 1. So that will be over here. One, one, one. Let's take the next value. Value 3. So we are at index I now. Binary value is going to be added to 3 left shifted by 1 into the block size 3. So 3 left shifted by 3. When you take 3 and left shifted by 3, you're basically appending 3 zeros at the end and then going for 1, 1 over here. And this is what 3 looks like, and this is what the left shift operation does. So what we are doing is we are adding this value over here to this value. So first 3 are 0, so that makes no difference in binary. And then you have 0, 1, 1. So that is 0, 1, 1. These didn't change because it was 0, 0, 0. Okay, and now you can probably understand why there is this left shift operation. Because we are skipping these bits. We don't want to touch these bits. We don't want to corrupt them. Logically, this is 7. This is 3. And now we come to this part where I is equal to 2. You come here, I equal to 2, A of I gives you 4. And you have I into B, which is 2 into 3. So 4 now is left shifted by 2 into 3, which is 6. So you have 3 more zeros now at the end. And this number has changed to 4. So that would be 1 and 0. Interesting. Yeah, I don't even know my binary values. So it's 1, 0, 0. Thank God it's written over here. So yeah, you take this entire thing. So that's a lot of zeros. 3, 3, and 2. So 8 zeros. So you see here, 8 zeros and then a 1. And as expected, you have logically a 4 over here. But you see that instead of using 32 into 3, which is 96 bits, we have just used 9 bits and we have shown 3 numbers till now. What about the third index, the final index? Binary value is set to whatever it is plus 6 left shifted by 3 into 3. So that is 9 bits to be skipped. 9 bits are skipped, and then you put the 6 over here. So what is 6 again? I could have skipped rubbing this 0, but okay. So this is your new array, so to speak. But it's a single value. Because there are only 12 bits in this, you can actually represent this using a 16-bit data type. And in Java, integers are 32 bits, but that's much better than using 4 ints. Instead of using 4 ints, you're just using 1 int. And that's a lot of savings. Okay, so this is an example where you're converting a 2D array or a 1D array to a single number. But what if you can't do that? What if there are too many numbers in your 2D array? Or what if the maximum value is so big and the product of the numbers and the maximum value, maximum bits required to represent this number is so big that you can't represent it using a single number? Let me just clarify everything. If you have an array which is quite big, let's say 10,000 elements, there's no way that you can fit that into a single integer or long or whatever. That data type is not big enough to store that much information. It will require 10,000 bits, which no sensible language contains as a data type. So you'll need multiple longs or ints to represent that matrix. And in that case, you'll need an array of binary values. Okay, so in this case, a single binary value was enough to represent our matrix, but there will be times when you need an array, and let's talk about how we can do that. So we have the more interesting case now, where we have fixed size data types, each of size 4. So integers usually have about 32 bits in Java, and Boolean has one long as 64. But in our theoretical scenario, we have 4 bits per data type, and it's our old example again. You just have these 4 elements with block size equal to 3. So you need 3 bits to represent one of these. And remember, we need 12 bits in total. So we need 3 of these data types to represent our entire array. Okay, now interestingly, binary value is an array now, as you can see. And the code has also changed a bit, so let's understand that. Binary value of I into b, what does that tell you? Of I into b tells you the information that you needed till now to represent the array up to this point. So I into b is that. Divided by data size. So each block can contain data size amount of bits, and the total information that you have till now is I into b. So total divided by how many blocks you needed up to this point will give you the index of the result, binary value. Alright, that makes sense. Plus equal to, this is an operator often used. Plus equal to means that whatever values on the left hand side, so a plus equal to b means that whatever values on the left hand side should be assigned the same value, a plus b. Right, this is just programming language syntax. That's it. We are just adding whatever is on the right hand side to the left hand side value and then assigning it to the left hand side value. So this is just a short form, and I was running out of space. Even now it's untidy, but it's alright. So this left hand side value, this block index is found out using this formula. Plus equal to a of I. So the element at that index, left shifted again by I into b, similar to last time, but mod data size. Now why is that? The reason you have this is because I into b gives you the total number of bits you need to skip. This divided by data size gives you the number of blocks that you need to skip. But now that you have skipped all those blocks and you know the number of bits also that you have to skip. So let's say you need to push something in here. You need to know that for this block, how many bits do I need to skip from the right? So how many bits do I need to skip from the right will come by total number of bits that you need to skip, I into b, excluding these blocks which are behind you. So that is given by the remainder. So that is modulo size of each data block, which is data size. Right, so what we are essentially doing is finding out where we need to insert our element and also finding out how many bits we need to skip before inserting our element. Right, this part is a little new and this part is also slightly new, but both of them are very logical if you take your time to understand what's happening. And let's just run through the code to understand it better. Alright, so firstly, we have 7. So 7 comes in, this is going to be a happy scenario because at 0, I into b is 0, this is also 0. So a of I is what is assigned here. 7 is equal to 1, 1, 1. There's just 4 bits, so I'll write it cleanly. 1, 1, and 1. Now we come to 1, and this is where things get a little tricky. 1 requires 3 bits. You come here, I into b becomes 3. 3 divided by 4 is still 0, so you should go here. And then you have a of I, which is 3, left shifted by 3 modulo 4, so that is 3 again. So we have binary value of 0 plus equal to 3 left shifted by 3. Okay, so we have 0, 0, 0 here, 1, 1, 0. This is equal to this value. And the first block has to be added to this. There's a problem. This value is larger than the number of bits which can be contained by this block. So what we are going to do is use a little more binary manipulations and convert this plus operator into an OR operator. Right. This makes a difference because when you are doing a plus operation, it means that if there is an overflow, the data type goes into negative values to compensate for that. Right? But when you do an OR operation, it's entirely binary. So if there is any overflow, it's excluded. So what do we get with that? We get skip 3 bits and put in 1 here. So 1 comes here and 0, 1 are skipped because they don't fit into the data type. So they are just excluded. Remember, plus will give you a wrong answer because then it will try to actually add this number to the 1 0 0 0 and that will create an issue. Alright, so this is what we want. Or do we? We lost these 2 bits. And that information is critical when you're actually coming over here. So when you're going for the next element 4, you need 2 bits over here and then 4 to actually come in here. In fact, 4 will also get mangled and go to 2 different blocks. So how do we take care of that? What you need to do is have a counter. Every time you are adding these bits to the blocks, you're also having information about how many bits you're skipping and how many bits you're adding. So the number of bits you're skipping is this quantity. Just mark that in red. This is the quantity that you're skipping. And B is the quantity that you're adding. So if I into B mod data size, write that down. Blue. I into B mod data size plus B, if that is greater than data size, then you have a problem, then there is an overflow, and in that case you need to actually go for the next index. You already have the current index, you need to go for the next index and take the remaining bits, which is this over here. Just get some space over here. Number of bits that you need to still take care of is given by this quantity minus this quantity. So data size is over here and I into B mod data size is here. Right? These are the number of bits that you still need to take care of once you have done this operation, this initial operation. So these many bits are what you need to take care of. You can store this value, the index value, and increment it by 1. So that will be binary value index plus 1 plus equal to, oh yeah, better not make that mistake, or equal to. These are the number of bits that you need to take care of, which means that you've already taken care of some bits which you can skip, right? And here's where things get more and more complicated when you get into binary. You need to take care of these many bits. So what is block size? 3. Block size minus number of bits that you need to take care of. So let's call this X. Block size minus number of bits that you need to take care of is what you have already taken care of. So already done. The already done bits should be skipped. You should lose that information. You shouldn't go on appending that. You don't want to be putting this one over here also. Right? That's what we want to avoid. So we need to know how many we need to get rid of. So you take your element, which is 3 now. You take 3, 1, 1, 0, and you right shift by the amount already done. This will make you lose some information. necessary to have the matrix in the right form. So you right shift, in this case, already done will be equal to 1. So you right shift to get this number, 110. You lost this bit, this single bit. Alright, so your new value now needs to be put into the index plus 1. I don't know why I didn't write it. So index plus 1 will have this new value ORed with it. So that is equal to 0, 0 and 1. 0, 0, 1. Just write it nice and neat. Okay. Similarly, you come to the second element. Again, you find out its index. It'll fall over here, which has index equal to 1. So yeah, I can write 8 because that's fine. Index is equal to 1, so you fall at this position. You need to put the information over here in this block. So that is equal to 100 needs to be put in this. After skipping how many bits? Well, if you take the I into B mod data size, it'll come out to be 1. So you skip 1 bit. No, it'll come out to be 2 actually, yeah. So you skip 2 bits. So it's over here. You see that 3 can be formed using these 3 bits. 7 can be formed using these 3 bits. And these 3 bits should logically form 4. So you skip 2 bits and then again you perform the OR operation, which gives you 100. So what you have here now is 0 and 0. And the 1 which should have come over here is lost, because like we lost the 0 and 1 over here, the 1 is lost in this scenario. With the 1 skipped, you again come back to this procedure which tells you I into B. So that is 2 into 3, 6 mod 4. That is 2. 2 plus 4, which is 6 again. So 6, if it is greater than data size, yes it is. 6 is greater than 4. So we need to do this procedure. 6 minus 4 gives you 2. 2 are the number of bits that you need to take care of, which means 4 minus 2, which is 2, are already done. So 2 bits are already done, as we expected. And now 2 bits are already done. You need to take your value 100, right shift it by 2, which gives you 1. You are appending these 2 zeros, but this is the new thing that you need to OR with the next index over here. Alright, I went through it pretty fast, but you can have a look at it slowly and understand why this entire thing makes sense and why this will then make the entire representation concise. Alright, so we have 0, 0, 1 to be ORed into this. Let's do that. So 0, 0, 1, and you can see now that this is 4. These 3 bits form 4. 1, 0, 0. Alright, finally we come here with the number of bits that you need to skip equal to 1. How's that? Well, I into B is equal to what now? 3 into 3, 9. 9 mod data size 4 gives you 9 mod 4 is 1. So yeah, 1 bit is skipped, and then you OR this index I into B, which is 9 divided by data size, which is 2. So 0, 1, 2. This is the index that we need to go to. What comes up here? 7 is ORed with these 3 bits. So 7 is 1, 1, 1. And therefore, finally, we have converted this array into an array of binary. So we have converted potentially 4 ints into really concise representations. Okay. In fact, our theoretical data size is pretty good, so it's just 4. But instead of using 4 into 4, instead of using 4 into 4 bits, which would have been 16 bits, we are using just 4 into 3 blocks that we have. 4 bits each, so that is 12 bits. So those are savings. And practically, of course, this is just to keep things concise and easy for me to write. Practically, you're saving, instead of 32 bits, maybe just you're representing in 3 bits or 2 bits. So usually you have huge data savings. So now things are going to get tougher. We have this set S which is of size n, and people can either exist in the set or not exist in the set. So they can either be alive or dead in a way. So if they're alive, then it's a 1, otherwise it's a 0. What we need to do is, for any given index, find out if that person is alive or dead. And this set is going to be represented using binary. So single bits are going to represent one person. Okay. So we'll be defining our set using this single binary number. It has 12 people in it, and the zeros and ones represent whether they're alive or dead. So what if you want to find out if the person at index 6 is alive? So let's go for some simple operations. How to find out if a person at index I is alive? All you need to do is set all other indexes to 0 and set the index at I to 1. Take these two numbers and them. If the result is not equal to 0, then that person at index I is alive. Otherwise they're dead. That's all. What do you do if you need to make the person at index I alive? Well, take the same number and OR it. So this is an OR operation. Store that in the result. The person now is alive, because OR actually sets it to 1. What happens if you want to make that person dead? This is more interesting. You want to kill them. So you're going to AND them again, and not just AND, you need to negate the entire thing. So AND negate this entire thing. So this will be all ones now, and this will be a 0, and this will be a 1. So the same number that you had earlier, when negated, turns to this, and then when AND with this is going to actually keep all values except the index that you're looking at. It's going to set that to 0, and you're going to be basically killing the person at index I. What if you want to set an entire block to 0? Just that block. So what you could do is find, you need a block of 1s basically, and a block of 0s in between. So you need blocks of 1s and blocks of 0s. So this is no longer just a single element, it's a block. So let's go for some simple operations. How to find out if a person at index I is alive? All you need to do is set all other indexes to 0 and set the index at I to 1. Take these two numbers and them. If the result is not equal to 0, then that person at index I is alive. Otherwise they're dead. That's all. What do you do if you need to make the person at index I alive? Well, take the same number and OR it. So this is an OR operation. Store that in the result. The person now is alive, because OR actually sets it to 1. What happens if you want to make that person dead? This is more interesting. You want to kill them. So you're going to AND them again, and not just AND, you need to negate the entire thing. So AND negate this entire thing. So this will be all ones now, and this will be a 0, and this will be a 1. So the same number that you had earlier, when negated, turns to this, and then when AND with this is going to actually keep all values except the index that you're looking at. It's going to set that to 0, and you're going to be basically killing the person at index I. What if you want to set an entire block to 0? Just that block. So what you could do is find, you need a block of 1s basically, and a block of 0s in between. So you need blocks of 1s and blocks of 0s. So this is no longer just a single element, it's a block. What you could do is take this block, what you should do is start from the reverse. So you have a block of zeros, you need a block of ones, and you need a block of zeros again, and you just need to negate this to get this the value that you want. So have a look at this. These many are zeros. That will be, let's say, p. P number of zeros is what you require on the right hand side. So a single left shift of size p will bring these many ones to the left. P to the left. So now first what we need to do is negate, and we are backtracking now. From here we need to left shift, and now let's backtrack to a block of zeros and just a block of ones. Let's say the size of this is b. So you need a block of b ones. What is 2 raised to the power b in binary? Well, that is nothing but just having 1 here and zeros here. So exactly as 1 left shifted by b. This is the number that you have. Bitwise manipulation. What happens if you subtract 1 from this number? If you subtract 1 from this number, this digit and the MSB is going to turn to 0, and every digit after it is going to turn to 1. So you now have a block of size p set to ones. And so from here, from the start, this position, we can then left shift, negate that, and then AND with the original result to set an entire range to 0. Alright, that's how you can use bitwise manipulations. There's lots of other stuff. You can find out what the MSB or the LSB is. I'll be sharing relevant links in the description below. But what I really want you to do is appreciate how awesome this could be. It really helps reduce the space complexity and sometimes even allows you to do computations that you couldn't do otherwise in your program. So try it out in your next contest, and I'll see you next time. Thanks.